This is Dr. Elliot Hollifield, and this is a video lecture for MAT 1070 covering Chapter 5.3 on logarithmic functions. Let's first define what we mean by a log function. We discussed previously what we meant when we have an exponential function. Let's write an example. Say we have 2 to the x. It turns out that a logarithmic function is defined to be the inverse of an exponential function. And so the inverse of this function, we'll call it f inverse, is the log base 2 of x. And so that means that the graph is determined. We can draw 2 to the x. Looks something like this. We know this ordered pair is 0, 1. And we know the domain and the range. The domain is from minus infinity to positive infinity, and the range is from 0 to positive infinity. Now for the inverse, we need to flip these. The domain becomes the range, and the range becomes the domain. So the domain for the log will be from 0 to positive infinity, and the range will be from minus infinity to positive infinity. Notice here that we also have a horizontal asymptote for the exponential function, and that will flip. Remember, we get the graph of an inverse function by flipping over this line, y is equal to x, and so the horizontal asymptote becomes this vertical asymptote. This point, 1, 0 goes to, or 0, 1 goes to 1, 0, and now we flip this graph over, this dashed line, and the graph of log base 2 of x has to look something as such. Up here, we have 2 to the x. Down here, we have log base 2 of x, defined to be the inverse of this function. And in general, if we have f of x is equal to b raised to the x power, and b is not equal to 0, then f inverse, the inverse function of this exponential, is defined to be the log base b of x. And now what is the key property that we have? Remember, if we compose an inverse function with the original function, then this gives us x. That says that the log base b of b raised to the x power is equal to x, and that b raised to the log base b of x is equal to x. These are key properties that we will need in order to solve expressions involving logarithmic and exponential functions. So now, using this property of the inverse functions, let's take this exponential equation and let's rewrite it as a logarithmic equation. Here the base is 4. So let's say that we have the log base 4 of x is equal to y. And now let's raise both sides of this expression as the exponent on the 4th power. Now using the inverse property, this says that x is equal to 4 raised to the y power. So how can we then use this idea in order to rewrite this as a logarithmic expression? Here we have 4 raised to the 3 power is equal to 64. 4 raised to the 3 power is equal to 64. Now I want to go in this direction and rewrite the expression as a logarithmic. The base will be 4. Think of taking the log base 4 of both sides of this expression. That is, the log base 4 of 3 will be equal to the log base 4 of 64. And now on the left-hand side, we use the inverse property. The inverse property says that if we compose them, we'll get this number back. This must be equal to 3 on the left-hand side. So we take this expression, we take the log base 4 of both sides. The left-hand side just reduces to 3 by the definition of the log as the inverse to the exponential. And the right-hand side reads as the log base 4 of 64, which means the same thing as 4 to the 3 power is equal to 64. Now let's try the same game with this example. Here, let's take this logarithmic expression and rewrite it as an exponential equation. We can think of taking 6 and raising it both to the left and the right hand sides. On the left hand side, the log and the base, they cancel. So we're just left with 1/6. On the right hand side, we get 6 raised to the -1, which we know to be true. Let's try some more examples here, going in both the forward and backwards direction, from exponential to log and from log to exponential. Here the base is 2, so let's raise 2 to both sides of this expression. These cancel, and we get 1 over 32 is equal to 2 raised to the -5. Over here, let's take the log base 7 of both sides. That says that the log base 7 of 7 raised to the 1 power is equal to 7. Log base 7 of 7. Here these cancel, we left with 1 is equal to the log base 7 of 7, which means the same thing as 7 raised to the 1 power is equal to 7. Now let's take it a step further and rewrite these equations involving a variable as logarithmic equations in the first case and as an exponential in the second case. Here, the base is e. Whenever we have the base e, we will call log base e of x equal to the natural log of x. And remember, e is just some number. E is a number which is around 2.1759, and the decimal keeps on going. So let's take the natural log of both sides of this expression. It says that the natural log of e raised to the 4th power is equal to the natural log of x. Now natural log and e cancel, and we get 4 is equal to the natural log of x. Now we have our equation rewritten as a logarithmic equation. Here we have the natural log of 8 is equal to y, so let's take e as the base on both sides. So e to the natural log of 8 just becomes 8. The right-hand side is e raised to the y power. Now let's actually evaluate some of these expressions. Here we need to remember this property that we have, that the log base b of x is equal to y if and only if x is equal to b raised to the y power. So the log base 5 of 1 over 5. 5 to what number is equal to 1/5? 5 raised to blank equals 1/5. What number must go here? Well, 5 raised to the 1 is 5. 5 raised to the 0 is 1. Must be a negative number, so this must be -1. 5 raised to the -1 is equal to 1/5. Now for the second example, we have log base 2 of 32. So 2 raised to what number is equal to 32? Well, I know that 2 times 2 is equal to 4, times 2 is equal to 8, times 2 is equal to 16, times 2 is equal to 32. So how many 2's do we have here? 1, 2, 3, 4, 5. 5 times. So the answer here must be 5. 2 raised to the 5 power is equal to 32. So the log base 2 of 32 is equal to 5. Now we have the log base 2 of 1. So 2 raised to what number is equal to 1? Well, here, if we have an exponential equation and the right-hand side is equal to 1, then it must be 0. Now we have base 5. 5 raised to what number is equal to 1 over 25? Over here on the right-hand side, we have a fraction. So 5 raised to what negative number will be equal to 1 over 25? 5 times 5 is 25. So this one must be minus 2. Now we have some logarithmic equations, and our goal here is to determine what is x. Let's take each of these equations and solve for x, keeping in mind that we have this tool rewriting this as an exponential equation. So the log base x of 10 is equal to 1/3. That means the same thing. Thinking of this side as a power of x, this side, raise that. So now the left and the right hand sides as the exponent on the base x. The left hand side becomes 10, the right hand side becomes x raised to the 1/3. Now we want to solve for x. So let's take the cube root of both sides. Cube root of 10 is equal to the cube root of 1/3, or, oh, gone in the wrong direction. One-third power. Let's rewrite this. This means the same thing as x raised to the 1/3 means the same thing as the cube root of x. So now let's cube both sides. Go in the right direction here. Now what do we get? 10 cubed will be equal to the cube root of x cubed, which is just equal to x. So this is 10 times 10 times 10, or x must be equal to 1,000. Now for the second example, we have the log base x of 1 over 81 is equal to minus 2. That means the same thing as 1 over 81 is equal to what base x raised to the negative 2 power? Here, let's remember what we mean by this negative. This means the same thing as 1 over x squared. So we have 1 over 81 is equal to 1 over x squared. Now let's do a cross multiplication here. That says that x squared must be equal to 81. Now, take the square root of both sides. Really, we'll get a plus or a minus case, but we need to eliminate one of those. Square root of 81 gives us 9. Now, should this one be positive or negative? Here we have this base x. Plug it into a log. Here, we need all of these bases to be positive. Technically, when we solved this equation, we got the positive and the negative case because we took the square root here. But really, we can only take this positive case. Now, we're given the graph of a logarithmic function. Our goal is to translate this to become a graph log base 3 of x minus 2 plus 1. So we'll have two translations here. The first translation, we'll have to deal with this x minus 2. We need to shift to the right by 2. Then this plus 1 outside of the log gives us a shift up by 1. So if we know this ordered pair, we also know this ordered pair, 3 raised to what power is equal to 1. Here we have the ordered pair 3, 1. The log base 3 of 3 is equal to 1 because 3 raised to the 1 power is equal to 3. Now we have these two ordered pairs. Let's shift them to the right and then shift them up by 1. Shift right by 2, 1, 2, and then up by 1. So this ordered pair now lives here. Now we shift this ordered pair to the right by 2, 1, 2, and then up by 1. Now we have our two ordered pairs. Let's also keep track of our vertical asymptote. We need to shift that to the right by 2 units. Now our vertical asymptote has to be here at x is equal to 2. Now let's draw our graph. It has to go up from the vertical asymptote and through those 2 points. Up through the vertical asymptote and through those 2 points. And now we have a quick sketch of what our graph should look like. Should get close to this vertical asymptote and then smoothly go through those 2 points. Now let's start with just an expression and determine the graph. Here, remember, we have a function, so we have the ability to choose x values and then to calculate the corresponding output. But we need to make a clever choice so we can actually do the calculation. Here we have the base 1/3. So let's think of our equivalence. 1/3 raised to what power will be equal to x? Just thinking of this piece here, because we have the base 1/3, and so an equivalent expression will be 1/3 raised to something is equal to x. So what will happen when we plug in -1 here? If we fill in this blank here with -1, that's this fraction raised to the -1 power. That gives us 3, and so x is equal to 3. So if I put a 3 here for x, then this blank must be -1. So let's plug in +3. Then 3 is equal to 1/3 raised to what power? That must be -1. So this gives us 2 minus 1, which gives us 1. So what other numbers would be a good choice to plug in? What if x was equal to 1/9? Then 1/3 raised to what power is equal to 1/9? That would be the square power. So if x is equal to 1/9, then the log base 1/3 of x is equal to 2. And so we get 2 plus 2 is equal to 4. Now, what are some more good choices? We have to pick numbers. Remember what the domain of these expressions is. It's from 0 to positive infinity. So we can go ahead and put our vertical asymptote here on the graph. Oh, that's a -2, isn't it? Let's correct those calculations. We have our vertical asymptote here, so we have to pick numbers which live to the right of this vertical asymptote. So here we get -2 minus 1 or -3, and here we get -2 plus 2 or 0. Let's see, what if we picked x is equal to 9? Now, 9 is equal to 1/3 raised to what power? Well, it'll have to be negative, and it'll have to be squared. And so it'll have to be -2. So we need to do -2 minus 2, which is equal to -4. Let's go ahead and put these points on the graph. We have 3 minus 3. We have 1/9, a little bit less than 1 is equal to 0. Then we have 9, comma, minus 4. And now can you see the shape of what this must look like? Here our base, 0 is less than the base, b is 1/3, is less than 1. And so the exponential function corresponding it lives up here. So if we flip that over, the logarithmic, the inverse, has to live down here. So it must be asymptotic to this vertical asymptote and then go smoothly through those points. Now we've got a nice quick sketch. Let's try another example where we determine the graph of this logarithmic function. Again, the difficult part is to determine what x's should we plug in to get a few points on our graph. And the trick is to use the correspondence between the exponential and the logarithmic. Log base 2 of x is equal to y if and only if x is equal to 2 raised to the y power. So what if we picked x is equal to, let's see, what's a good choice? Well, let's first pick 0 for x. Oh, no, we can't pick 0. Let's pick 1 for x. If x was equal to 1, then 2 raised to what is equal to 0. For these logarithmic functions, we're always going to get this ordered pair, 0, 1. We're also going to have a vertical asymptote here at the y-axis. And we have to pick x values which live to the right of this vertical asymptote. Now let's pick, say, the number 4. Then if x is equal to 4, 4 is equal to 2 raised to what number? Well, here it has to be 2. So that gives us this ordered pair, 4, 2. So first we picked 1 and the output was 0. Now we pick 4 and the output is 2. 4, 2. Now, graph will have to go from this vertical asymptote smoothly through those points. So now we have a slightly more complicated looking expression here. We have the natural log, remember that is log base e, of the square root of 2x plus 9. And we want to find the domain of this function. What numbers can we plug into this expression? Well, if we have a natural log, then we already know the domain is from 0 to positive infinity. And so that means that we need the square root of 2x plus 9 to be strictly positive. Now let's square both sides. That says that 2x plus 9 square root quantity squared is bigger than 0 squared, or that 2x plus 9 is bigger than 0. Now let's subtract 9 from both sides. 2x is greater than minus 9, and now let's divide by 2. That says that x is bigger than minus 9 over 2, which we can write in interval notation as open bracket, open parenthesis, minus 9 over 2 to positive infinity. Let's try another example. Here we have the log base 1, or the log base 10 here. Whenever you see a log, and there's no number written here, we think of this as the log base 10. Here again, the domain of log is 0 to positive infinity, so now we need x squared minus 1 to be strictly positive, which means that x squared has to be bigger than 1, and thus x has to be, there's going to be two cases here. When is this true? Let's draw a number line here to help motivate this. This is -1, here will be 0, here will be 1. What numbers can we square and have the output be bigger than 1? Well, for example, -2 times -2 is 4. That's bigger than 1. And so any number that lives to the left of -1 will actually satisfy this inequality. And then any number that lives to the right of 1 will satisfy the inequality. That is, we have these two pieces. Either x is strictly less than -1 or x is bigger than 1. That gives us this interval in interval notation, minus to infinity to -1 and from 1 to positive infinity. So now let's try graphing this function where we have several different translations of the function log base 2 of x. Let's go ahead and first just draw the graph of log base 2 of x. So in this color, I will put the graph of log base 2. We know it goes through this, always goes through this ordered pair, 1, 0, and also goes through 2, 1, has this vertical asymptote, gives us a graph that looks something like that. Nice quick sketch. Now in a different color, let's put the graph of 1/2 log base 2 of x -3 -4. So let's see. We're going to have a scale by 1/2, a shift to the right by 3, and a shift down by 4. Scale by 1/2, shift right 3, down 4. So here we have the two ordered pairs on our original graph. The first was 1, 0, and the second was 2, 1. Now we're going to shift those ordered pairs first by scaling the y value by 1/2. So if we scale 0 by 1/2, that stays at 0. If we scale 1 by 1/2, that becomes 1/2. So 1, 0 goes to 1, 0 under the first translation, and 2, 1 goes to 2, 1/2. Now, what will these other two translations do to those two ordered pairs? Now we're going to shift these ordered pairs to the right by 3. Now we're shifting these ordered pairs. 1, 0 will go to 4, 0. 2, 1/2 will go to right by 3, 5, 1/2. Now we need to shift those ordered pairs down by 4 units. Now we work with these ordered pairs. Now 4, 0, that will go to 4, -4. 5, 1/2 that will go to, let's see, 5 comma subtract 4 minus 3.5 or minus 3.5. Now we have our new ordered pairs. Go to 4 comma minus 4, one here, and 5 comma minus 3.5 right here. We also need to graph our vertical asymptote. We had an asymptote at 0 before, now it'll be shifted over by 4 units. No, over by 3 units. So our vertical asymptote will be here at x is equal to 3. And then we need our graph to go through those ordered pairs. Nice quick sketch. So our last topic here is to consider a change of base for logarithms. That is, what if we want to rewrite our logarithm into a certain base so that it's easier to do the calculation? So as long as we have these numbers, a, b, and c, and a and c are not equal to 1, then we have this formula. Where over here we had the log base a, and we pick the new base that is not equal to 1, we can rewrite this log in terms of this new base. So now our goal here is to evaluate the log base 7 of 8. We're going to do that by using our change of base formula. Most calculators will either only have the base b equal to 10 or e. And remember that the log base e is the natural log. So we could pick either of those, either 10 or e, to change this one. And so we know what a and b is. A is equal to 7 and b is equal to 8. Let's use c is equal to 10 in this case. So now we use our formula. This will become the log base 10, which is just written log of b divided by the log base 10 of 7. And now this is in a form that you can plug into most scientific calculators. Now let's change this one here. Have the log base 1/3 of 8. And so a is equal to 1/3, b is equal to 8, and now let's use c is equal to e. We'll use the natural logarithm. Our change of base formula says this will become the natural log of 8 divided by the natural log of 1/3. And now we've put this one into a form that you can plug it into the calculator. And I'll let you do both of those calculations. Lastly, we have a somewhat complex looking formula that we would like to solve for what is x. Let's see, we have the log base 1/4 of 17 raised to the x plus 2. And we want to solve for x. And so here we have this really nice property of logarithms and exponential. If we have the log base, let's say a, of b raised to the x, then this is equal to x times the log base a of b. In a sense, this x just comes out front and becomes a multiplication. And that's exactly what we'll do here. Our exponent is x plus 2. So if we rewrite that using this rule that says that x plus 2 times the log of 1/4, log base 1/4 of 17 is equal to 19. And now we can divide both sides by this log term to get x plus 2 is equal to 19 divided by the log base 1/4 of 17. Now we can subtract 2. 19 divided by the log base 1/4 of 17 minus 2, and now we can even use our change of base formula to put this into a form that we can plug it into a calculator. So here is our change of base formula. Let's copy that over to here so we can apply it to this problem. So let's see, A is 1/4 in this case, B is equal to 17, and we can either choose the C to be 10 or E. Let's choose 10 in this case. So we have A is 1/4, B is 17, and let's see, C is equal to 10. So now let's use that to rewrite our expression. We have 19, and we're dividing that by log base 1/4 of 17, which we can rewrite as the log base 10 of 17 divided by the log base 10 of 1/4, and then we subtract 2. So now we've rewritten this into a form where we can plug this into a calculator and get our decimal approximation. And so I'll let you do that calculation.